Hi, I'm Nathan Hunt, and I'm going to be presenting on our work, Verifiably Safe Exploration for End-to-End Reinforcement Learning. Reinforcement learning systems have recently made significant progress in effectively learning to control complex systems, even from raw inputs such as images from cameras. However, learned controllers can't be used in many critical settings without having safety guarantees to ensure that these systems won't perform actions that could hurt the system or people around it. Formal methods can provide safety guarantees, but these methods haven't been applicable in environments with visual observations. Our objective in this work is to be able to train a reinforcement learning controller end-to-end in visual environments while providing safety guarantees even during training and exploration. The setup for this problem is that we have a Markov decision process as usual in reinforcement learning with a given set of states, actions, initial states, and a transition and reward function. In addition to the usual setup, we also have safety constraints, which are specified in terms of a higher level symbolic state space. Because the original state space of the environment is the low-level image space on which safety constraints can't effectively be specified. Only those parts of the environment that matter for safety need to be included in this symbolic state space. And a domain expert provides a safety constraint which takes in the symbolic state and an action and returns true if and only if that action is safe to take in that symbolic state. As a running example, we'll use this simple adaptive cruise control environment. This is a one-dimensional environment where the follower robot in blue should maintain a safe but close distance behind the leader robot in red. The state space of the environment consists of images like the one shown here. However, the symbolic state space instead has the positions of the two robots and the relative velocity of the follower robot. In practice, we use a stack of images instead of just one image as the observation, as is usual in reinforcement learning, to allow estimation of things like velocity by the reinforcement learning agent. Our approach to safety, which is based on that of Fulton et al., constructs a verified monitor. This is useful because rather than verifying the policy, which changes throughout the learning process, we can verify the monitor once before reinforcement learning begins, and then use it to screen the actions of the learned policy and only allow those actions that are safe to be taken in the environment. If an unsafe action is attempted, some method is required to determine which safe action to take instead, and we'll get into that later. As Fulton et al. Did, we also use differential dynamic logic to express the environment dynamics as well as the safety constraints to be satisfied and the properties of the initial set of states. The Chimera X verifier is used to verify that the safety constraint will be satisfied as long as the monitor is obeyed. This is a quick overview of differential dynamic logic. This logic uses hybrid programs to specify both continuous dynamics in the form of differential equations as well as discrete dynamics, such as the reinforcement learning agent changing the action that it is taking at discrete points in time. So alpha and beta here are hybrid programs, as I just described. And in differential dynamic logic, hybrid programs can be chained using the semicolon operator, or a non-deterministic choice between programs can be executed. One program can be executed a non-deterministic number of times. Variables, such as x here, can be assigned to any real value or to the evaluation of some term, some polynomial, for example, of different state variables. Or we can specify a system of differential equations according to which the state variables evolve, which ends if at any point the domain F would not be satisfied anymore. And we can also abort if a formula is not true, which, if used after a non-deterministic choice, only aborts those choices for which the formula does not hold, but allows all other choices to continue. Formulas, such as F in the domain constraint or the abort condition, can be constructed as conjunctions, disjunctions, implications of other formulas, or using existential or universal quantifiers, or comparisons between polynomials over the state variables, or using the box operator here, which means that the formula phi holds after all executions of the hybrid program alpha. Returning to our example system of adaptive cruise control, the plant or the environment dynamics can be specified in differential dynamic logic as shown here, where x is the position of the follower robot, whose time derivative is v, and the time derivative of the velocity is the acceleration, which is the action that the controller can set. Small t here is the time elapsed since the previous control decision, and big T is the maximum amount of time that is allowed between control decisions. For simplicity in this example, we will also constrain that the velocity is greater than or equal to 0, which makes the safety constraint somewhat simpler for presentation. The abstract controller for this environment is that the acceleration may be set to any value such that it's within the bounds minus b to a, which are the maximum braking force b, or maximum deceleration, and the maximum acceleration a, and such that the safety bound holds for whatever the control decision is, where the safety bound is as shown here. The formula for the initial conditions is shown here, which just ensures that the follower robot at least has one safe action that it can take when it begins, which is to brake as hard as possible, as well as that the various parameters of the environment, such as the maximum deceleration and acceleration and the time between control steps, are all positive, and that epsilon, the separation required between the lead robot and the follower robot, is also non-zero. Finally, what we verify is that if we begin in a state where init is satisfied, then following the abstract controller here, and then the evolution of the environment given by plant for any number of steps will always lead to the safety property that the separation between the lead and follower robots is greater than epsilon being satisfied. We can use Chimera X to verify that this property does indeed hold, and then we can use this safety bound given here to ensure that our reinforcement learning agent never causes the follower robot to collide with the leader and becomes unsafe in this environment. However, we can't apply the verified monitor directly because it requires symbolic state information, such as the locations of the robots and their velocity, which is not present in the observations from the environment. Therefore, we use a model based on CenterNet to extract object locations from the observations. The object detector performs a pixel-wise classification to determine if each pixel is the center point of any of the classes of objects to be detected. And additionally, from each center point, there's a regression for any other object parameters that need to be identified. So as we've shown here, from the center point pixel, we estimate the width and the height of each object. This allows us to construct a bounding box around it, so we know how large the objects are and how far away their center points thus need to remain in order for the objects to avoid colliding. In order to minimize the labeling effort for these visually simple environments, we just require that at least one image of each safety relevant object be given and a background image. And then we construct a synthetic data set by pasting these images together and using various augmentations that are common in computer vision. From this data set, we can train the detector before reinforcement learning begins so that we'll be able to use it to be safe throughout the reinforcement learning process. Because we're using a visual system, we'll need to make some sort of assumptions about the errors that it makes in detecting object locations if we want to be able to guarantee that we can act safely. We begin with a very simple assumption that all detections are bounded by some known epsilon. That is, all safety relevant objects are detected and the distance between their detected locations and their true locations is at most epsilon. We estimate the epsilon value from the synthetic dataset before we begin reinforcement learning. We'll discuss later more general noise models that could potentially be used instead. And here's an example for this synthetic dataset of the label image that we use when we're training the classification task for the follower robot here in blue. Now that we've extracted the symbolic states and verified our monitor, we're ready to begin reinforcement learning. The monitor can determine if the actions are safe, but it has no idea which safe action to take. So reinforcement learning will give us a policy that can take actions that will optimize for reward in different tasks. However, we quickly run into the problem of what to do when the reinforcement learning agent attempts an unsafe action. We can find a safe action using the monitor to take instead, but we have to decide what feedback to give to the reinforcement learning agent for its learning process to continue. And what we propose is to put a safety wrapper around the environment, and we'll show you how this is constructed. So given the original environment E, which was a Markov decision process, we construct a new MDP E prime with the same set of states, initial states, and actions, but with modified transition and reward functions. Because we don't know ahead of time which actions would be best to take in any given state, we'll have the safety wrapper replace any attempted unsafe actions with a safe action sampled uniformly at random from the set of safe actions for that specific state. This leads to the following transition function for the safety wrapped environment, and also to this reward function. For simplicity, we assume here that the action set is discrete and finite, but in practice, in our environments, most of them have continuous action spaces, and the results here apply there as well. We show that acting in the wrapped environment has the following properties. None of the actions are unsafe, because any action which is unsafe in the original environment is replaced with a safe action in the wrapped environment. And following any policy in the safety wrapped environment corresponds to acting with a safe policy in the original environment, which has the same action transition probabilities and the same expected rewards over its trajectories. And thus also following any optimal policy in the safety wrapped environment corresponds to following a policy in the original environment which is optimal among all safe policies. These properties allow us to learn in the safety wrapped environment without the agent and the reinforcement learning algorithm needing to know about the fact that we have a monitor that is replacing some of our actions. So all of the safety aspects are put inside of the environment wrapper, and we can use any reinforcement learning algorithm off the shelf. Here is an overview of how this system works, where the actions come in from the controller to the safety wrapped environment and go first to the monitor, which determines, based on the symbolic state that is extracted from the observations using the detector, whether the actions are safe. If they're safe, then the controller's action is passed to the real environment. If not, then a safe action is sampled, and that's passed to the environment instead. And the observation and reward associated with the action from the monitor are then returned to the controller. So as far as the reinforcement learning algorithm is concerned, there is not a monitor or a detector or any replacement of actions. There's just a slightly modified MDP, but whose reward function still allows you to learn the optimal policy in the original environment among the safe policies. Finally, we'll proceed to the environments that we introduce in this work. And we have 4 different ones, which try to highlight different aspects of the relation between safety and reward optimization. So the first environment is the only one with a discrete action space. So here the dynamics are just that the agent, which is the plus in the center of this image, can move left, right, up, or down. The safety constraint is that the agent must avoid colliding with any of the O's, and the reward function gives +1 for X's and -1 for any O's. What is interesting about this environment is that because of the tight placement of the objects in this grid, if the agent is too conservative about avoiding colliding with the O's, it won't be able to pass through them to collect all of the X's on the other side. The next environment is the adaptive cruise control one that we've seen before, where the action is to set the acceleration of the follower robot. The safety constraint is that it must avoid colliding with the lead robot, and the reward is proportional to the negative distance from a point that is close to the lead robot but slightly behind it, which is set up as the ideal point to maintain for cruise control. What's interesting in this environment is that when safety is enforced, even a very simple policy can get a good reward here. So in this environment, we can see how being safe or enforcing safety can speed up the reward optimization process. And unlike in the example, we do allow the follower robot to have negative velocities here as well, and we have safety constraints that handle that. The next environment is a goal-finding one. Here the dynamics of the robot are a little bit more complicated. It chooses both an acceleration and an angular velocity, and then follows the dynamics shown here. The agent must avoid colliding with these red hazards that are spaced throughout the map, and it receives a reward based on its distance to the green goal, and a discrete reward also when it reaches that goal and the episode ends. In the point messes environment, the dynamics of the agent are the same, as are the safety conditions, that it must avoid colliding with the red obstacles. The reward, however, is different for this environment. It's modeled after a Roomba type task where the agent needs to move around and clean up these X's in blue that you can see in the observation here. And what's interesting about this environment is that colliding with any of the red obstacles, rather than ending the episode, will result in the obstacle breaking and releasing a number of small point messes around the obstacle location that can be cleaned up for reward. So this environment has a sort of reward hacking behavior that the agent can take, where it can purposefully create more mess in order to be rewarded for cleaning up that mess. So here we see that enforcing a safety constraint can help prevent that type of reward hacking behavior. It's also worth noting that because the safety constraint is the same in this environment, and the only difference is in the reward function, that the same detector and verified monitor can be applied in the goal finding and point messes environment. So we see here how only requiring that the safety relevant parts of the environment be in the symbolic state space lets us use the same safety system for multiple different tasks in the same sort of environment, where only the reward function needs to change between tasks. Now we'll show our results in these different environments. The baseline reinforcement learning algorithm that we use is proximal policy optimization, which is a popular recent reinforcement learning algorithm that has performed well in many environments, especially for visual reinforcement learning tasks. And first we show for each environment the number of unsafe actions taken by each method over time. So in blue we can see that PPO takes a large number of unsafe actions in all of the environments, even more so in some than others. And even once it's begun to converge and learn a fairly good policy, it still continues to take unsafe actions some of the time. VSRL, on the other hand, is successfully able to remain safe throughout all of training and takes 0 unsafe actions in any of the environments. Next, we look at the results for reward optimization. So for the first 2 environments, PPO is able to learn a pretty good policy by the end of training for XO and for ACC, though the results are much noisier in the ACC environment. And in both of these, VSRL is able to learn a better policy and to learn more quickly, as we expected in ACC, because enforcing safety makes it so much easier in that environment to learn not to crash into the lead robot when you're remaining close to it. VSRL is able very quickly to learn a good policy, and in the XO environment, because the environment wrapper removes the need to penalize the agent for being unsafe, it doesn't become overly cautious, and so it's able to explore and acquire all of the X's in the environment and achieve the optimal amount of reward, even though it has to get near the unsafe O's to do so. In the final 2 environments, the goal finding and point messes environment, the baseline method, PPO isn't able to successfully learn a policy to perform these tasks well, and so VSRL remains safe but also doesn't converge to a better policy. Finally, some future directions. First would be to loosen some of the assumptions. So recall that we made the assumption that for the object detection, there's at most a distance of epsilon between the detected and actual object locations, and that all safety relevant objects are detected in every frame. This would require a very good detector and is probably not feasible in practice. However, if an unsafe object can get to the agent without it being seen at all, then we won't ever be able to guarantee safety. But perhaps an error model in the middle might be that any object will be detected at least every certain number of frames, or it will be detected once it gets close enough to the agent. Another of our assumptions needed to verify safety was that the dynamics need to be known ahead of time, and that can be difficult, at least to have perfect dynamics. So future work could either work to learn the dynamics from scratch or to learn a modification of dynamics given by a domain expert to help adapt them to what's actually seen on the real system in practice. One drawback of our safety wrapping method is that the wrapped environment will now have more complex dynamics near unsafe regions because of this sampling of which safe action to take to replace unsafe actions that are attempted. It would be nice instead if we could take those safe actions that would make learning or reward optimization easier, perhaps using a hierarchical reinforcement learning method to have a different policy for acting near the unsafe regions that could quickly learn how to move around the obstacles. It would also be interesting to try to internalize the safety constraints, so the monitor is still being used even after training has been completed, and continuing to use the monitor isn't a problem, but if there is some degree of error in the specification of the dynamics or of the safety bounds, or an unexpectedly large error with the detector, the agent might be able to still remain safe if it can generalize safety somewhat. So supervised learning, such as imitation learning, could be used to try to set the agent's probability of unsafe actions to 0, because we know which actions are unsafe in any given state, so we don't need to rely on reinforcement learning for that. However, we'd have to be careful if training an agent this way to avoid becoming overly cautious. So in summary, our contributions are that we present a method for enforcing high-level formal safety constraints on reinforcement learning agents, which are trained in visual environments. And we present a theory showing that safety can be preserved entirely on the environment side with a safety wrapper around the environment, allowing any reinforcement learning agent or training algorithm to be used without needing to modify it to incorporate safe behavior. And we also present a set of new environments for testing safe reinforcement learning from visual inputs with known dynamics, which highlight a set of different aspects of the relationship between preserving safety and enforcing reward. Thank you.